know each other for a long time, and he's one of the top experts on quantum noise, which is like a really highly relevant subject in gravitational wave detectors. So, Stefan, it's yours.
Okay, I hope you can hear me. I can hear myself, that's good. Yes, so thank you for having me here. It's a big honor and a pleasure to be in Brazil. This is my first time. And today I will be giving you an overview of what is actually this kind of thing, quantum noise, and why it is at all important. So as I was instructed by Jan, the whole purpose of this enterprise is to raise awareness, or basically advertise the importance of gravitational wave science to the Brazilian researchers. And before starting this, I just referred to the Volker's lecture, where he talked about one particular very small, if you think about it, part of the detector, which is basically the Faraday isolator. So there is nothing more important for advertising as to advertise the personal benefits. So I will tell you a bit of a story, very short. So basically this small thing was started to be developed in the Institute of Applied Physics in Nizhny Novgorod. So they basically provided the first prototype of this to LIGO. And then, after the detection of gravitational waves, the first person who gave the interview on the national television in Russia was the director of this institute. And he was announcing the detection of gravitational waves. And 1.5 years later, he was elected the president of the Russian Academy of Science. So you see, it's very important to do instrumental science in LIGO. Okay, so to quantum noise. I have a great responsibility to finish before the closing, or actually opening, of the launch window. Okay, so what I will be talking about is, first of all, the motivation, quantum noise in gravitational wave detectors, why bother? Then the grand plan of the campaign is outlined here. So I will start with the origins of quantum noise and where the quantum limits, this is the most important thing because that limits our sensitivity, arise. Then that is actually deceptive. So there will be one slide, I think, or two slides, where I will talk about the moving to the frequency domain and spectral densities, how it is important, but probably you already know about it. So, and then this part is probably the one which will be sacrificed to the more noble endeavor of having a lunch. Okay, so quantum noise, why bother? So basically, you have seen this picture already, I think, at least 2 times. So this is the theorist view of how the noises in LIGO, in advanced LIGO, look like. So, and you can see that the black curve, which is overall total sensitivity, design sensitivity of LIGO, is very close up to roughly 20 hertz, 15 hertz, upwards to the magenta one, which is the quantum noise. So the next closest in this frequency region is the thermal noise, but that I leave to Yuri Levin and Katsuhira. So, and at lower frequencies, quantum noise is not that relevant, at least for advanced LIGO, because of the other, most importantly, the seismic noise and the gravity gradient or Newtonian noise, of which you will hear how to deal with this from Ettore and Jan. Okay, so now you see that the advanced LIGO, should it go to the design power, circulating power of 800, I think, maybe 750, I don't remember what is now the official number. Basically, 3/4 of megawatt of circulating power. Then it will be limited by quantum noise in almost all of its detection band, from 10 Hertz and upward. So this means that the next generation of detectors that we want to build, and this is a workshop about the future, so it should have at least order of magnitude better sensitivity, and that actually immediately implies that you should do something with this noise, which limits you in here. So the question is, can you do it, and how can you do it? So the answer to that is basically the gist of my lecture now. So the clever quantum noise mitigation techniques. But before that, I will try to explain how it works, this quantum noise, and what it is, and how it limits the sensitivity of the detector. So again, my version of a very familiar slide. So you have the Michelson interferometer, but Volker did already all the work. And what this thing actually does, so it measures the phase shift between the two light waves which travel to the end mirrors and being recombined at the beam splitter. So in principle, if the lengths are equal, then you should get the perfect destructive interference, and you have no light on the photodetector. But if there is a phase shift between these two waves, so you get some power detected by a photodetector as a result of the interference. So interference is the device or means by which the phase is transformed into power that you can measure. So that's it. The gravitational wave detector is a phase meter. Good. Okay. So, and what exactly is quantum about the gravitational wave detector? So if you think about it, that the interaction of gravitational wave with the mirrors, or if you are a disciple of a TT gauge, George, then of the refractive index for the light in the arms. So this is a completely classical process, so there is nothing quantum in it. So the gravitational wave signal is transformed into the phase shift of two lights. So the interference happening here is also a classical effect, so there is nothing quantum in it. So photodetection is actually quantum. This is where light is transformed into the discrete flux of electrons. And that actually manifests that light itself is also consisting of the particles, of the photons. But at the same time, it is a wave, because it has all of these classical features. So this is where quantumness comes into play. So, and then the question arises, so are there any implications for detection accuracy from the fact that we have a quantum light? And yes, there is actually, and that is encompassed by the photon statistics of the laser. So basically, what is the statistics, quantum statistics of the light, which is generated by the laser? And Volker has given a very nice introduction, how many things actually come into this, again, theorist understanding of what is laser. But I will not do that, so let's go on. And then there is another important thing, which also was mentioned in Volker's lecture, is that the interaction of light with the mirrors is also quantum. If you think about the light as being flux of photons, then you will understand that the light will also have a mechanical action on the mirrors. Okay, so, and this all boils down to this formula, which is the uncertainty relation, the Heisenberg uncertainty relation, but written for phase and number of quanta, which are the two conjugate observables of light in quantum mechanics. So, and if you transform this into this form, you will see that the accuracy for your phase measurement, and remember that interferometer is a phase meter, is limited by the uncertainty of the number of quanta which you detect on the photodetector. So, it all will be very good. So this curve, also shown by Fall curve for the photocurrent at the photodiode, which is so smooth and nice, and also the smooth and nice sinusoidal waves in here are not actually what you have in reality. So the light is not so pure as we might think, but instead it's this hairy and fuzzy kind of thing, which is the representation of electromagnetic wave in the coherent state. So if you try to measure the amplitude and phase of this sinusoidal wave, which is a light frequency, I should say, so it's very high frequency one, then in principle, you will find out that at every moment, it has a fluctuating amplitude. There is a mean one, which is this red dashed line. This is the mean classical wave that you would study in classical electrodynamics. But around it, you have this forest of fluctuations of amplitude and phase. And if you draw this picture on the phase plane, where you put the amplitude and phase quadrature as the coordinates, so you basically get this red one as a vector pointing at some point and rotating clockwise. But the measurements that you will do, many of them on the amplitude and phase, will give you basically this fuzzy blob around the center. And this is actually the manifestation of quantumness. So you have a fuzzy blob. So what to do with that? So yeah, so actually I should have said that the amplitude and phase can be, so there is where quantumness is coming into play. So you basically put hats and introduce the ladder operators, creation and annihilation operators. And that is how the amplitude and phase quadratures of light are expressed in terms of them. So this is a basic quantum optics which has no importance for understanding what I will tell later. So forget about it. Oh, so we have a glitch. Oh, it was a reminding that I should finish as soon as possible. Okay, so to understand quantum noise in the interferometer, let us consider a simplest possible system, which is just a suspended mirror with the light reflected over it and some magical device which measures the phase of this light. Of course, there is much more real things involved into measuring the phase. You need a local oscillator and probably a balanced homodyne detector, but this is not the point here. So the motion of the mirror is reflected in the change of the reflected light phase, which will be 2 multiplied by the wave vector of the light, which is 2 pi over wavelength, and multiplied by the displacement of the mirror. So 2 in front is because light goes 2 ways if the mirror is displaced by delta x. So the light goes 2 delta x. So then measuring the displacement of the mirror precisely means that we need to discern the state of the light, the phase basically of the light, for the initial point when there was no displacement and for the new point when there was a displacement. So on the phase plane, this boils down to the motion, to the rotation of this fuzzy blob on a stick. And to measure this displacement of the fuzzy blob on the phase plane means that you need to discern whether this fuzzy blob has moved or not. And the accuracy of that is apparently the size, the diameter of this blob. Yes? I will come to that. So let's assume that there is some force, gravitational wave, for example, or any other force that you want to measure, your signal. So, and this is causing the displacement. But that is a very apt question. I will come to the radiation pressure on the next slide. Yes. So, this picture doesn't take into account the radiation pressure. So this is, again, a classical, but invoking that there is some phase fluctuations. So basically, this is the amplitude of your laser, and the orthogonal direction, and then here is the phase fluctuations. So it's a jitter of the end of the vector according to the quantum statistics of the laser light. So this circle here is the coherent state representation in the phase space. Okay, so what the measuring this displacement means, so you basically need to measure this angle. And you can measure it if these two fuzzy blobs do not overlap. So the one before the displacement and the one after displacement do not overlap. So apparently, this angle becomes smaller and smaller because the size of the blob doesn't change if you increase the length of the stick. So, and the length of the stick is basically the amplitude, which is the square root of the power, or the energy, number of photons. So, and this is giving you the quantum uncertainty, which is also known as a shot noise. So this is the shot noise, which indicates just the phase fluctuations, the fundamental phase fluctuations of light. And in principle, it is the sensitivity of your device is limited by 1 over square root of number of photons you send. But this is, as you aptly pointed out, is not the whole story, because the photons having uncertainty also in the amplitude quadrature. So they basically give a random kick to the mirror and make it move randomly. So this is radiation pressure noise. And it adds some noise displacement to the mirror. So, and interestingly, this transformation of amplitude fluctuations or intensity fluctuations into the displacement and from the displacement to the phase, so that causes the state of light, which is reflected of this moving mirror, to be not a coherent state anymore. So it actually gets squeezed. So I don't think we have time for this, but this effect is known as a ponderomotive squeezing. So, and it comes from the fact that the radiation pressure is actually proportional to the intensity of light, and intensity of light is quadratic in the light electric strain. So in principle, interaction of the mirror with the light is a Kerr-kind nonlinearity. And therefore, this, a very specific one, I should say. So this effect produces squeezed light I will be talking about later, and the one which Volker was talking about in his lecture. Okay. Did I say yes? Okay. Radiation pressure noise. So 2 parts. If you add them up, what you will get is that at low frequency you will have a noise dominated by exactly this radiation pressure, and at higher frequencies you will have the phase fluctuations of light, just the quantum state of the laser light coming off the laser, defining your sensitivity. And it's important, yes, that the radiation pressure is actually proportional to the power, and therefore the phase fluctuations it produces, additional phase fluctuations, are proportional to the number of photons, while the phase fluctuations are inversely proportional to the number of photons. So the overall error will be the sum of these two, where one term is 1 over square root of power, and another additive term is proportional to power. As a result, there is always a trade-off, and this trade-off is this black line, which is a locus of all possible sensitivities depending on which power you send to your to your mirror. And if you decrease the power to decrease the radiation pressure noise, it will decrease, but the short noise will increase proportionally. And likewise will happen if you increase the power to decrease the radiation pressure, to decrease the short noise. It will cost you the increase of the low frequency part. So, and all these curves will actually touch this black line, which is known as the standard quantum limit. Oh well, let us go into more quantitative details about that. Okay, so coherent state. So this is a picture you can find in every book on quantum optics. So what basically it tells, so it tells that the state, the photons in our light beam are actually following the Poissonian statistics. So which means that the mean number of photons, or the variance of the number of photons is proportional to the square root of the number of photons. That's the only thing I need from the Poissonian statistics. So, and as a result, the short noise we can estimate to be equal to this, but I have told about this already. So how it actually relates to the gravitational wave detectors where we always talk in terms of the laser power. So the number of photons in the laser beam can be calculated from this simple formula. So it is the power divided by the energy of one photon, which will give you the rate, the photon rate, n dot, and then multiplied by the measurement time gives you the number of photons, the average number of photons. Okay, so that's it. Yes, so that I already covered. So, and using this formula and the previous formula for the uncertainty of delta phi, which is 1 over 2 square root of n average, you can derive this formula for the displacement uncertainty. So basically, you take the phase uncertainty and recalculate it in displacement. So now, more complicated thing, the back action. So the back action is the photons kicking the mirror randomly. So while kicking, they transform twice of their momentum. Each of the photon transfers twice this momentum. And the overall momentum transferred is actually this, is 2 multiplied by the number of photons by the momentum of one photon. So, and then you can immediately calculate the uncertainty, randomness basically of this momentum transfer, and that will be expressed by this formula. So, and this means that this mirror, if we assume that it is a free moving mirror, then the displacement caused by this momentum transfer will be just this momentum multiplied by the time over which it was moving, so basically the time of our measurement, divided by the mass of the mirror. So this is how we calculate the back action, or the displacement caused by the back action. And then we add up the two things, and we have this formula, that we can optimize over the power. So again, you see that the shot noise is inversely proportional to the power, and the radiation pressure is proportional to the power. So we have a very, okay, so it should have actually recompiled, but anyway. So you have a over some variable plus b multiplied by variable. What is the minimum of this function? It can be calculated that this is 2 multiplied by square root of coefficient in front of both. And this is the SQL. So this is the formula of the SQL given in this paper by Braginsky of 1967. So it says 68 because this is the English version. It was published in the obscure Russian-speaking journal. Okay, so that's it about the quantum noise and how it works in the very simple, in a nutshell. So what is a takeaway message from here? So the quantum fluctuations of light phase and amplitude is the quantum noise. So the ones which you can reduce even further because of the laws of quantum mechanics. So phase uncertainty defines the precision of the measurement, which is known as the shot noise, and it is inversely proportional to power. And amplitude fluctuations create random radiation pressure or back action force, which scales proportional to power. That mimics the gravitational wave signal. So the trade-off between the two gives a standard quantum limit. So I hope that is now, after I repeated it 3 times according to the laws of pedagogic, so should stay. Okay, now what actually happening in the frequency domain? So you can imagine that what is happening in gravitational wave detector is basically when the mirror is moving, what it does on the light, it modulates the phase. So this is the motion of our mirror, and this is how it is changing the otherwise just a monochromatic wave. So this is the phase modulated wave. So, and if you move from the time domain picture to the frequency domain picture, so this one corresponds to just one delta function at the frequency of your laser. So the spectrum of this motion of the mirror is looking like this. When it is imposed through the modulation onto the carrier, so you get a carrier with the 2 sidebands, upper and lower sidebands, modulation sidebands, and this is actually your signal that you want to measure. So, and all the frequencies you see in the sensitivity curves is actually the frequencies which are calculated from this point, which is considered as 0, up here. So it's actually upper sideband frequency. Okay, yes, I said that. Oh, one more thing. So actually, it's interesting that motion of the mirror creates 2 photons, one on the upper and one of the lower sideband. So effectively, this is a 2-photon process, and therefore the mathematical formalism, which deals with the calculation of quantum noise, is known as the 2-photon formalism. Yes, of course, it creates it creates 2 photons out of 2 photons of the carrier. Yes, that's true. But it always takes 2 photons. So that is why it is 2-photon formalism. But of course, you are right. So, and if you add the quantum fluctuations of phase and amplitude, that is also a modulation, a random modulation. And what is important for us is the modulation. Yes, okay. So it's the modulation of our signal of sidebands at all frequencies. So instead of this nice smooth picture, you basically have some hairy noise on top of it. And the whole purpose of gravitational wave science is to get this shape out of the noise. So here it is actually shown like a very high signal to noise ratio. But in reality, it's mostly noise. And it is also important to say that here it doesn't depend on the frequency, the magnitude of the noise. But in reality, the sensitivity curves actually show you how this noise changes as it goes from the carrier frequency upwards. Okay, so and this is exactly what I just said. So this is the sensitivity curve. So forget about this dash dotted lines, just the gray one. So this is the typical sensitivity curves of the Fabry-Pero-Michelson interferometer in the units of strain. But how it is, well, this is the answer to the question which Volker asked. So why it is going up in here? It is because the Michelson interferometer with Fabry-Pero's so doesn't actually sense any phase modulation above the cavity pole, which is the bandwidth of the Fabry-Pero cavities in the arms. So and this is here. So and this is the response to the gravitational wave, the response of the interferometer to the gravitational wave. So and this is how the quantum fluctuations of light looked like. So this is the shot noise. It is frequency independent. And this part is what actually is introduced into the phase by the radiation pressure. So it grows up to lower frequency as 1 over frequency squared. So and this curve is obtained by dividing this one by this one. And as a result, here, because of this frequency, yes, it's 1 over frequency squared, no, 1 over frequency slope, it goes up here. Oh, good. How am I doing? Okay, we're still on schedule. Good. So that is what I wanted to say, that gravitational wave manifests in modulation sidebands at frequencies, modulation frequencies capital omega, which is much, much smaller than the light frequencies, the laser frequencies omega naught. Quantum noise shows up as at all sideband frequencies as random phase modulation, and quantum noise strength with respect to gravitational wave signal at each frequency is expressed by the strain sensitivity curve. So by dividing one by another, by the response. Okay. Okay. Yes. So this is the quantum noise in gravitational wave detectors in a nutshell, with omitting all the dirty details, as people say, swiping it under the carpet. But basically, this is how it works. So there are much more to that, but I will not talk about this. So what should you do to suppress these quantum noise fluctuations? And there are many ways to do it. And here we go from the simplest one, which it has already found implementation in gravitational wave detectors. So you modify the quantum statistics of your light. And this is adding or generating a square vacuum and injecting it into the detection port. So there are several variations how you can, and problems, I will talk about this. So just the squeezing doesn't help. You actually need to have different squeezing at different frequencies. And then there is a most modern proposal which has 3 magic letters EPR, which stand for Einstein-Podolsky-Rosen correlation. So this is a magic path to high impact publications. But anyway, so I will also talk about this. Not about the magic path. It's classified information. So not everyone should get into nature. Okay, then you can modify the outgoing light to evade back action. So this approach is known as variational readout, And there is also a new fancy way, which I will not talk about unless somebody asks. So it's a negative mass spin-based filters. Very fancy name, but okay. So here you actually have an expert who has written a paper. It's Yuri Levin, one of the authors of the famous Kimball-Levin, Matsko, Thorne, and Vichanian paper, who invented this variational readout for LIGO. Okay, so what else can be done? So you can change the state of the light not outside of the interferometer, not feed the interferometer with squeezed light, but as you heard, there are many laws involved in getting the light, the squeezed light, injected into the interferometer, but you generate the squeezed light directly inside the interferometer, which sounds like a very promising way of doing things. Apart from that, generation squeezing means that you put in the interferometer a rather lossy, non-linear crystal, and all the problems with mode matching and absorption and scattering and stray light suddenly start to play tricks with you. But anyway, this is a very promising way to go because it avoids any loss in the injection stage. And then there is a white light cavities. So the original version of it invoked some even worse, putting some atomic medium with a negative dispersion into the interferometer. So it was very nicely summarized by one of my colleagues, quantum noise working group chairs of the LSC, over my dead body. So there are problems. I am not telling you all the truth about it. So just indicating that there are. Then you can actually go even further and design the way you are measuring gravitational wave. Instead of measuring the displacement of the mirrors, and this is my topic, so you actually built a new topology of the interferometer, which is known as a speed meter. So you detect the gravitational wave by measuring the relative speed of the change of the arms. Why it is better, we will probably hear soon, or maybe not, or maybe we'll go for lunch. And finally, this is one of the old ways. Basically, the standard quantum limit depends on what kind of system is your mirror. So thus far, we considered that the mirror is just freely moving, which means that, of course, it is actually a pendulum. But this pendulum has a frequency, and I think Ettore will definitely talk about this in his talk, at around 1 hertz. So it's below 1 hertz. So it's very slowly oscillating pendulum. So if you look at this pendulum at the frequencies much higher than the oscillation frequency, the natural oscillation frequency of the pendulum, it's a free mass. But if you somehow increase the frequency to the detection band, to say 100 hertz, then you have an oscillator. And oscillator has a resonance feature. So basically, any force that acts on the oscillator at its natural frequency causes a huge surge of the magnitude of the motion. So, and this is actually the modification of dynamics, but in interesting way. So, because just increasing the magnitude, the frequency of the suspended mirror doesn't work, because it will bring all the thermal noise of the suspensions into the detection band. So instead, it was proposed to use an optical spring. So basically create a spring with a light. And it was demonstrated experimentally that it is possible. But again, if you ask about it, the people on the sides, they will say roughly the same as my distinguished colleague said. Because that requires to detune the interferometer from the resonance condition, which leads to a huge amount of difficulties, like all the control noise start to get into your detection signal. And so basically, I will not talk about this because there are specialists in this that could hold me accountable for what I say. Okay, so let's start with the squeezing, because I feel compelled to tell what Volker promised that I will tell. So basically, if you remember this fuzzy sinusoid, which I have shown for the coherent state, so this is actually how the squeezed vacuum state, vacuum means that there is no classical component, so it's a wave with a zero amplitude, but it will have this interesting noise, modulated noise, which is actually the manifestation of rotation of this ellipse. So you see that the photon statistic is squeezed in one direction and extended in another. So extended exactly to the same amount as it is squeezed here, so as to keep the uncertainty in accordance with the Heisenberg uncertainty principle to be minimal. So squeeze states are the minimum uncertainty states as well, like a coherent state. So this one is the amplitude squeezed bright state. So bright state means that there is a mean classical amplitude. So, and this is the representation of the phase squeezed state. So this how it will look if you were able to make a an ideal experimental device that will show you this oscillogram. It doesn't exist at optical frequencies, so just figments of theorist's imagination, but very useful for pedagogical purposes. Okay, so how do you create the squeeze state? So it turns out that actually the nature gives us a perfect tool for that, which is nonlinear crystals. So nonlinear crystals which have the polarization that depends not only linearly on the electric strain of light going through, so it polarizes, the electromagnetic wave goes through the crystal, polarizes the molecules of the crystal, and it turns out that for certain, actually all of the materials have a nonlinearity, but it just depends on how big is the second coefficient. And just for the scale, you can have a look at the numbers, and these numbers you can find, for instance, in the in any nonlinear optics books. So this one, I think I took from the Robert Boyd's one, very nice one. And it is related to the intraatomic electric strain. So basically, all of these coefficients depend on the on the electric strain between the electron and the nuclei. Anyway, so you have a polarizability that is proportional to the square of the electric field of the light wave. It will result to the following thing. So if you put the light, the pump into the crystal, so the nonlinearity will create two photons, signal and idler. So I think it should be actually not 2 omega p, just omega p equal to omega s plus omega I, because this is the energy conservation, basically. So the frequencies of the two created photons, the sum of the frequencies of the two created photons should be equal to the frequency of the pump. So, and this is how you actually, in reality creates squeezing. Okay, so what it will lead to, so if you have a squeezed light, yes, squeezed light, and you put it on the beam splitter and mix it with the local oscillator, and you change the phase of the local oscillator, what you will see on the difference current of the photodiodes is this thing. So if you sweep the phase, and if you don't sweep the phase but choose the optimal phase, so that you basically detect the quadrature which is squeezed, that will be this blue. So it's a real experimental plot. You can see it. I took it from this paper. Oh no, actually I took it from Zeman-Chilkovsky's paper. And the black one is actually non-squeezed. So if you send just a vacuum, if you just don't send anything, basically. So that will be this. So and this is a manifestation of the squeezing. Okay, good. This is, I think, all about the, yeah, no, not all. So how does it help with the gravitational wave detection? Well, return to the fuzzy blob on the stick picture. And if you decrease the uncertainty in this direction, in the phase quadrature, so that's it. So it's much more easier to detect this angle. So that's how it works. And this is the experimental curve of the geo sensitivity, which shows that with the injection of squeezing, which is a 3.7 dB squeezing, well, I think injection was actually something like 7 dB, but because of loss, it was 3.7 dB. You see the improvement of sensitivity at high frequencies. You don't see any change at low frequencies, because at low frequencies, geo is not limited by quantum noise at all. Okay, but if geo was limited by quantum noise, the following will happen. So this is basically how the injection of squeezing looks like, and this is how theoretical people understand the Faraday isolators. So it looks like that in our mind. And if you inject phase squeezed light into the interferometer, so the sensitivity, so let me see, so this faint dashed gray curve represents the sensitivity of the interferometer without squeezing. If you introduce 10 dB squeezing to it, phase squeezing, then you get the blue curve. And you see that at high frequencies, you get the improvement of sensitivity. But at low frequencies, you basically get the same kind of thing as if you just increased the power. So the radiation pressure noise increases. And this is because at low frequencies, you actually introduce more radiation pressure noise, because at low frequencies, the ponderomotively squeezed light is actually amplitude squeezed, and it is rotated if you add more amplitude squeezing to the amplitude, more noise in the amplitude quadrature, because phase squeezed light actually has increased amplitude fluctuations. That increases the radiation pressure. If you instead try to reduce the radiation pressure noise with the amplitude squeezing, the result will be equally devastating, but at high frequencies. So this is the red one. So introducing just the frequency-independent squeezing. Frequency-independent means that squeezing angle is the same at all frequencies. Doesn't have much. But there is a clue that you can improve the situation if you inject some intermediate squeezing, for instance, pi over 4, at the angle pi over 4. Then you get this interesting looking gray solid curve, and you see that it goes in a very narrow band below the standard quantum limit. Can you do better and actually reach this red dashed line, which is the basically the 10 dB improvement of the original sensitivity of the interferometer. Yes, the answer is yes. And to do that, you actually need to use an phase squeezing at high frequencies, intermediate squeezing at medium frequencies around the cavity pole. Gamma is the cavity pole or bandwidth of the interferometer. And at low frequencies, you should create amplitude squeezing. So how do you do that? So, and what actually defines the angle of squeezing? Well, as a matter of fact, it's just a phase. It's the phase of your squeezed light. So changing the phase by 90 degrees, you will change the angle of your squeezed light, of your squeezing ellipse by 90 degrees. So that's it. So you need to introduce a dispersive element that changes or doesn't change the the phase of light at high frequencies, but changes it to 90 degrees ideally at lower frequencies. And oops, yes. So and here is this element. You just send the squeezed light to the interferometer through this cavity. It's a filter cavity, so it's a triangular one, just for simplicity, but in principle it's the same cavity as the Fabry-Perot in the arms. So it lets the light inside the cavity if the light is the modulation sidebands, if they fall in the bandwidth of this cavity. But it reflects everything which is above the bandwidth of the cavity. So if you send what we need to send, phase squeezed light, yes. In here, so at high frequencies above the bandwidth of this cavity, it will be just reflected and go directly into the interferometer and will produce this nice sensitivity. But the light which is within the bandwidth of this cavity, it will go inside and circulate for some time there and then get into the interferometer with some rotated phase. So, and you can choose the parameters of this cavity so that at low frequencies, it will be amplitude squeezed. And in the medium frequency, it will follow this curve, actually. This is the optimal dependence of the phase of your squeezed light. And as a result, you get the optimal squeezing in all frequencies. So this is how I think A+ will use a frequency-dependent squeezing. So this is what is called frequency-dependent squeezing, and it is basically the technique that is already in the design of all of the next generation detectors. Okay, so this is the paper of Yuri and Jeff Kimball and friends. So very nicely written paper, so you can read it. It's just a sheer pleasure to read. Okay, so yeah, dirt. So there is a problem with this approach because actually you need to have a bandwidth of this filter cavity pretty narrow, basically of the order of 100 hertz, where you want to have the highest sensitivity. And that, given that there are also losses in this filter cavity, is possible only if the filter cavity is fairly long, which means it's of the same length, roughly, as the as the arms of the interferometer. Well, you can make some trade-offs. So basically, you can even make it 10 times smaller, and it will still work just because of loss. So it will not look so nice. It will not have 10 dB at every frequency. Well, it will be good if it gives 3.5 dBs. But anyway, so, and injection loss. So basically, to expedite squeezing from here, from the nonlinear crystal into the interferometer, it's just enormous amount of optics involved, the injection optics. And each optical element is lossy. As a result, overall, for now you get something like 35, I think, % of loss, which diminishes the 10 dB squeezing at the output, even 15 dB is now possible, to a mere 3.5, I've already mentioned. Okay. Oh yeah, EPR squeezing. So it's ingenious idea, actually. And the gist of this idea is that we do not need to make a good filter cavity. We already have it. It's the interferometer itself. So the only problem is that interferometer is already occupied. So it is occupied by the carrier light. So how to actually mate the 800 megawatts, 800 kilowatts of power with the fragile squeezing? Oh, so these guys, Ichu and other people who wrote this paper, they come up with a brilliant idea. Oh, you just use the squeezer, but not in the regime, in the degenerate regime, where it generates squeezed light at the carrier frequency, but instead you slightly detune it in such a way that it comes non-degenerate regime and creates two beams of different frequencies. So this is actually the two frequencies, and you make the frequency difference between these two beams of the order of several megahertz, and then, because the bandwidth of the arm cavities is 100 hertz, maybe kilohertz, so actually this several megahertz means that this light, the blue one, the idler beam, will not see any carrier. So the carrier is sitting around here. But because of the nonlinear process of generating two photons at a time from the pump, so the two beams are entangled. So if you let the idler beam at several megahertz to go to the interferometer, for which it is completely empty, it doesn't see the carrier because it is several megahertz above, and you choose the detuning of this light with respect to the carrier frequency, to the resonance frequency of this airy resonance, it is actually falling within. So if you choose it right, then you can get the rotation of this idler beam, which is quantumly correlated with the carrier beam, actually, in such a way that when you measure it, it collapses the signal beam into the right squeezing angle that you want. So there is, of course, some penalty you have to pay, but basically these are the sensitivities that you can get, and different colors actually represent different levels of loss. So the price to pay here is that you have to separate these two different frequency beams using the at the readout, first of all, using the filter cavities, which are known as the output mode cleaners. You have to have two instead of one in the current detectors, and for each of them you need to set up an individual balanced homodyne readout. So which basically means that your readout loss is also increased by a factor of 2. So you lose factor of 2 in squeezing, because entangled beams actually individually have a penalty of 3 dB, and you increase the loss which you currently have in the squeezing enabled interferometer by a factor of 2 at least. 15, okay. Yes, I said this. Okay, so, and then the variational readout idea introduced in this paper is the following. So actually, if you look at what the light in the output of the interferometer looks like, it will be squeezed. So, and this is the reason why you have the radiation pressure noise. Radiation pressure noise is the manifestation of pondromotive squeezing created by the interaction of light with the mirrors. So what if you don't look at the phase quadrature, which is this direction, but instead you measure some combination of phase and amplitude along the direction where the magnitude of fluctuations in the outgoing light is the lowest. And it turns out that if you do that correctly at all frequencies, so here is the trick. So because this is the picture at one particular low frequency where the radiation pressure is squeezing your outgoing light in this way. At other frequencies, the amount of squeezing and the angle is different. So you have to adjust your measurement device in the right way at each frequency. And this is, again, can be done using the same old good filter cavity. But now, instead of putting it in front of the squeezer, you put it in the output of the interferometer. So you submit the, or you inject the squeezed light in the interferometer, and then you filter, or actually, I don't know if it is correct, but forgive me, it's a theoretical understanding of how it works. So basically, the outgoing light you send through the filter cavity, and the filter cavity presumably rotates the squeezing angle in the right way every time, and you do a balanced homodyne detection of it. So, and this is what you will get. So if you don't have the squeezing, so instead of the this sensitivity curve of the normal Michelson interferometer, without anything, you get the sensitivity, ideally, without radiation pressure noise at all. So this is a radiation pressure evasion or back-action evasion technique. If you introduce squeezing, you can get even better. But the devil is in detail, and this detail is actually loss. So if you have a very small loss in this stage, when you direct your light, squeezed light, very fragile, squeezed light, quantum light, in here, and every element here has its losses, so this is what you get. So actually, this technique is much more susceptible to loss than the squeezing, the input squeezing, or pre-filtering, as it is called. So unfortunately, the beautiful dream is very difficult to implement unless you find some way to deal with loss. Yes, this is what I said. Okay. Oh, so I still have some time. Do I still have some time? Yes, I do. Okay, so good. Okay, so now squeezing is covered. So, but is it the only way to do the business? So, as it turns out, actually, from the point of view of the high-minded quantum measurement theorists, it's the worst way to do is to measure the displacement of the mirrors, because displacement does not commute with itself. Yes, I'm saying terrible words, but it does not commute with itself at different times. And from the point of view of the quantum measurement theory, this is the perfect blueprint for failure. Okay, it means it cannot be measured precisely with arbitrary precision. So That's why there is an SQL. So, but already in the 30s, John von Neumann introduced in quantum mechanics the notion of the quantum non-demolition observables of the system, which are the observables that can be measured without back action being seen in the result of the measurement. So there is still a back action, but it is organized in such a way that it doesn't change the result of the measurement. Okay, so and as an example of the quantum non-demolition observable, one can introduce the momentum of the free mass. The momentum of the free mass, as we all know, is a conserved quantity. And being a conserved quantity means that if you are able to measure it, so you can actually measure it without any disturbance. Okay, so, and this principle was first proposed by these two gentlemen. Unfortunately, Professor Braginsky is now deceased, but this is my supervisor, Farid Khalili. So he's in good health and very active in science. So actually, this negative spin, mass spin here is currently being worked out by him. So as early as in 1990, they proposed the idea of measuring the speed, because speed is proportional to the momentum. Well, there is a trick, actually a flaw in this. But anyway, so the original idea was to measure the speed that will give us the access to momentum. So, and they explained it in the following way. So this is already a simplified version, because in 1990 paper it is written for the microwave readout of the of the bar detectors. At that time, it was considered that the bar detectors will be competitive, or actually it was the mainstream at that time. Anyway, so why actually measuring the velocity may help? So if you look at this thought experiment, so we want to measure the force acting on this mirror. So, and for this, we try to measure the velocity. Don't ask why we would measure the velocity, but believe me, it will benefit you in the end. So how to do it? So you basically reflect the light of the mirror once. So this light will carry the information about the displacement of the mirror at time t. So then you let it through the delay line and let it reflect of the rear surface of the mirror for the second time, which will give you the displacement at time t plus tau. And the resulting phase will be proportional, because of reflection of the front and the rear side. There is a minus sign here. The result will be proportional to this difference, which is a mean velocity of the mirror multiplied by the time between the two measurements. So yes, this kind of thing measures the velocity. But why it is good? If you look at what is happening here from the point of view of the back action, it's the following. So yes, in the first interaction, the photons kick the mirror in this direction, or in other direction, they are random. But the same very photons which kick the mirror, and they carry the same fluctuation of the momentum, will kick the mirror after some delay time from the rear, and will partly, just because there is a delay, will partly compensate the damage they have done. So there is a kick in this direction and the kick in this direction created by the same very photon. It has to be compensated. And this is why you actually can lower the radiation pressure noise with respect to just the measurement of the displacement. So the red one is the measurement of the displacement. The blue one is the measurement of the speed. So why don't you eliminate the back action completely? This is because if you measure the velocity, then you have a terrible drawback. Your response to the gravitational wave is actually reducing to 0 at the DC. So basically at low frequencies goes like that. But this decrease of the response, and the decrease of the response is understandable. So why it is proportional to the frequency? Because velocity is the derivative, time derivative of momentum. And in frequency domain, it means multiplying the spectrum of displacement by I omega, by frequency. So, and this is why you have the response, which is waning as proportional to frequency. But it is proportional to frequency, while radiation pressure force, if you calculate the power spectral density, is reduced by the frequency squared. So this plot is actually square root of the power spectral density. So it means that the reduction in the radiation pressure force is going down as frequency squared, while the response is going down as frequency to the power of 1. So quantum noise limited sensitivity in units of strain is the quantum noise divided by these. So the quantum noise going down, so it's basically constant, because radiation pressure noise of the displacement measurement goes up as 1 over frequency squared. The radiation pressure noise of the speed measurement is constant at low frequencies. So if you divide it by this response, the blue one, so what you get is actually the curve which is going much slower up at low frequencies, and it is following the standard quantum limit in principle. So, and you have this wonderful window where you have an advantage in sensitivity. And also you have an improvement at high frequencies just because your photons interact with the mirror twice. So, which is effectively meaning that you have twice the power compared to the same laser power of the displacement meter. So, and this is what you can get if you put all of the parameters into the large interferometer configuration. So the blue one is the Michelson, the red one is the equivalent speed meter interferometer for the parameters like LIGO, 4 kilometer, and this is like parameters for Einstein telescope. So this is also taken into account the frequency dependent squeezing. So it means that these two techniques are not orthogonal to each other. You can use them together, and actually to the advantage of the speed meter, the requirements for the filter cavities are much reduced because the radiation pressure that the filter cavity has to compensate is also reduced. Okay, good. So this is how you implement this in the gravitational wave detectors, and this is the current status of the speed meter field. So these are configurations that have been considered. Good. Okay, so, conclusions, great. So I made it on time. Okay, so read the conclusions carefully, and this is the sources of information that I highly recommend you. Okay, at least the first two. I highly recommend you to read. It's really good reading. Thank you.
Thank you. Okay, maybe we have time for one question before we go to lunch, if there's any. Otherwise, of course, the same holds. We can have discussions later.